Hello, and welcome to section 3.2. And you remember from last section, we looked at the rules for the derivative of the sum and difference of two functions. And the derivative of the sum is equal to the sum of the derivatives. But that's not the case with products. The derivative of the product is not equal to the product of the derivatives. And we can see that by this one counterexample. X squared and x. So their product is the function x cubed, and we know that using the power law the derivative of x cubed is 3x squared. But if we look at the derivative of the individual functions, the derivative of f of x is 2x, the derivative of g of x is just 1, so their product is 2x. Clearly 3x squared is not equal to 2x. So we know that we can't say the derivative of the product is the product of the derivatives. So we have to remember a special rule. So if f and g are both differentiable, then this is the product, the derivative of the product is equal to the original function, one of the original functions, times the derivative of the other function, plus the other function times the derivative of the first function. So you don't have to know how the product rule is derived to do the problems. It's nice to know and to kind of build your mathematical maturity. So where this comes from is actually thinking of the area of a rectangle. So because area is length times width, we have a product. So if we think about a rectangle that have sides of length f of x and g of x, then their product is the area. So if we can figure out how the area changes for a change in x, then we're on the road to finding the derivative of the product. So notice that, for a change in x along the x-axis, the value of g of x is going to change, the value of f of x is going to change, and so the area is going to change. So I'm going to define a function, f of x equals x squared is going to be the height of the rectangle. So the output values from f of x are going to give me the height, and the output values from g of x are going to give me the width. So starting with the point 1, 1, I see the area of my rectangle is 1. Now I'm going to look at what happens when I change x by a little bit. So dx is the difference in x. So if I change it by 1/2, 0.375, 1/4, 0.125, you see how the value of f of x is changing a little, the value of g of x is changing a little, and that area is changing. So we see how a change in x is going to affect the change in the area. So let's look at the area of these additional little rectangles that are formed when we've moved this point. The area of this rectangle has a width of dx and a height of f of x plus dx. And the width and the area of this triangle has a base of gx, and it has a height of f of x plus dx minus f of x. That's this dy. So that's how the area changes. So now let's make a rate out of it. So how does the area change per change in x? Well, that means we divide by dx. That's our change in x. So we want to see how is this area changing as this dx changes. And what's the derivative? The derivative is when that dx, the limit when that dx goes to 0. So I'm taking my areas, my new additional area that I got here that's outside of the original rectangle, and that's my change in the area, and I'm dividing it by dx. So notice that this looks like the derivative of g, the difference quotient, times f of x plus dx. And this looks like the difference quotient with f times g of x. So if we simplify that, or take these, factor it, we can see that there's the difference quotient for g, there's the difference quotient for f. And the whole point of this is getting that instantaneous change, so that means we're letting dx go to 0. So if we take the limit as this thing goes to 0, that's giving us the derivative of the area, which the whole point of this was because that's really giving us the derivative of the product of those two functions. And that's how we get the product rule. Okay, so now let's look at some examples of how you'll be using it. So differentiate this function. So before, even if we had multiplied the EX through, we still would have a sum of products, and we didn't know how to differentiate that yet from section 3.1. But now we do. So we can look at this first factor as a function, and this e to the x factor as a function. They're both differentiable, so we can use the product rule. So the product rule gives us the derivative of the first function, the derivative of f1, is simply 1 plus 2 times x to times 1/2 times x to the minus 1/2. So I use the power rule here after considering the square root of x as x to the 1/2. And then the derivative of e to the x is simply e to the x. So putting that together, the derivative of f prime is the derivative of the first factor times the second plus the first factor times the derivative of the second. Here's another example. So this function g of x might look a little scary, like it's a quotient, but we can always rewrite it by negating the exponent. So we're going to rewrite g of x as minus e to the positive x. So we're going to use the product rule, so we need to get the derivative of each factor. So f prime of x is 3x squared. G prime of x is just equal to g of x, because that's e to the x. So therefore, applying the product rule, the derivative of the first times the second plus the first times the derivative of the second gives us this function. And we're supposed to evaluate it at 3. And we'll just simply evaluate this function at 3. Now this example is a little different. We're being given g of x in terms of this other function f of x. We're supposed to find the equation of the tangent line to g at the point where x equals 3. So you know that we need to find the derivative of g because we're being asked for the equation of the tangent line. And of course the derivative at 3 would be the slope. So to find the derivative of g, we use the product rule. So we don't know what f of x is exactly, but we are given this information. And we know that we're going to eventually be evaluating g at 3. G prime of x is going to be the derivative of the first factor, which is just 1, times the second factor, f of x, plus the first factor times the derivative of the second factor, which is f prime of x. We don't know what it is, but we know it's f prime of x. So g prime of 3 is going to give us the slope of the tangent line at 3, so we can evaluate this guy. And we were given what f of 3 and f prime of 3 were, and that evaluates to minus 2. So we know that our tangent line has slope minus 2. And then we simply put in the other points. So this is the slope point form of a line, and this is the slope intercept form. And I wanted to tell you these examples are from the book, either even numbered questions or questions that they don't have coded in WebAssign that are good for you to do or see.